Galaxies Collide. I'm Dr. Frank Summers of the Space Telescope Science Institute, and I would like to thank my wonderful tech team, Thomas Marufu and Grant Justice, who are taking this meeting and sending it out over YouTube for you to watch. I note that we will be online only until further notice. Our upcoming talks include in March, the Hubble Space Telescope from Cosmological Conflict to Alien Atmospheres. This is Tom Brown, the head of the Hubble program here at STSCI, and he's going to give you a wonderful, wonderful overview of what Hubble has done over the last 30 years. On April 6th, Christopher Wanjak, an author, will be here to talk about one of his books, Spacefarers: How Humans Will Settle the Moon, Mars, and Beyond. In May, we have a really special treat for you. We have the Consonant Collective and the Bergamo Quartet of the Peabody Institute here in Baltimore. This is one of the premier music conservatories, and they will be presenting Finding the Music of the Spheres, Hearing Stars. It will not be just lecture, it will also be a musical performance. You're not going to want to miss that one. And if you want to find out, keep up with all these things, you go to www.stsci.edu/public-lectures. You'll find this webpage, and on the left, you can see you'll find links to our webcasts, both on YouTube and on the STSCI webcast archive, as well as you can sign up for the lectures announcements by entering your email address and hitting the subscribe button. Of course, you can find out information about the upcoming lectures, and if you click on one of those lectures, you will get the complete details, including the abstract of the talk, and after it has been presented, links to the STSCI webcast, as well as the YouTube recording. If you'd like to sign up for our email, I showed you how to sign up at the website, but you also might, instead of using the email, subscribe to our YouTube channel, youtube.com/all one word Hubble Space Telescope. This is where we post all of our videos as well as our live events. And if you subscribe, you will get notices of those new videos as well as reminders of these live events. Finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. We also have social media channels for both the Hubble Space Telescope, the James Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself do a tiny bit of social media on Facebook and Twitter as Dr. Frank Summers. And now the news from the universe for February 2021. The first story tonight, it was a dark and stormy night on Neptune. Now, for those of my generation, the phrase, "it was a dark and stormy night," is not associated with the novel at which it was the very first line, but it's really associated with Snoopy and Peanuts, because this is what Snoopy uses as his first line of his novel that he's writing. And that's the only way anybody in my generation actually knew of it. I'm told there was a book that actually included this as the first line. And in terms of storms, we can get some really stormy nights here on Earth. This is Hurricane Isabel. And Hurricane Isabel came through Baltimore about 15 years ago, and it was quite the stormy night there. But if you follow astronomy, you know that what we have on Earth really isn't that stormy, because you want big storms, you go to Jupiter. And Jupiter's great red spot, this big oval up here, that's a storm that's as large as our entire planet. And so you have this big orange storm here, and they've actually had observations of the great red spot for a couple hundred years. So it's not just a dark and stormy night, it's a dark and stormy centuries on Jupiter. And you can see that these white ovals are also storms in Jupiter. You get orange ones and red ones and white ones. But Neptune actually has storms that are dark. Yes, this is what's called the Great Dark Spot on Neptune. right? It was observed by Voyager in 1989 when the only space mission that has flown past the planet Neptune. And so we saw that there is a possibility of having these giant dark storms on Neptune. Unfortunately, it's not as long-lived as the Great Red Spot, because when Hubble looked in 1994, and this is images of both hemispheres of Neptune in 1994 from Hubble, the Great Dark Spot was gone. So these dark storms on Neptune form and obviously disappear. Hubble is the only telescope that has the keen resolution to be able to follow these storms. And in 2016, for example, we saw this dark storm on Neptune in its southern hemisphere. And the idea is from computer simulations that these storms will form at mid-latitudes, and as they migrate toward the equator, they will dissipate because they're sort of supported by something called the Coriolis force. You don't really need to understand that, just know that the Coriolis force goes away as you get to the equator, so that they might dissipate as they get to the equator. Well, Hubble has covered 4 dark storms since it's been watching. And the most recent one, here it is observed in January 2020. And you can see the large dark spot here. And on the right-hand side, you can see a smaller dark spot. Now, the large dark storm was discovered in 2018, and they followed it as it started to move towards the equator and presumably would then dissipate away. But in January 2020, when they looked, they found not only was there a second dark spot, but also that the storm had reversed direction and was now heading away from the equator. This is something that they had never seen. So the question is, well, first of all, why did it reverse direction? And second of all, is this second dark storm related to the first? I will tell you that we don't know the answer, but there is an intriguing hypothesis. Computer simulations show that these dark storms should actually break up every now and then and split into multiple storms. So this could be evidence that this storm was migrating towards the equator, started to break up, spawned off that smaller storm, and started to reverse direction. We can't prove that hypothesis, but they will be studying it continuously. Right? And as I said, Hubble is the only telescope that can resolve these storms and follow them. So over its 30 years, Hubble has seen 4 dark storms. So we really don't have a tremendous amount of information to work on. But every time we see one and every new data point we get tells us more and more about uncovering those dark storms on Neptune. Our second story. It's an episode of CSI SMC. Now, when I talk about CSI, I'm talking about crime scene investigation. This is a series of television shows, right? There actually have been several television shows. They take place in Las Vegas and Miami and in New York. Well, this episode of CSI takes place in the Small Magellanic Cloud, which we often refer to as the SMC. Right? It is a dwarf galaxy. It's a satellite galaxy of the Milky Way, the Small Magellanic Cloud and the Large Magellanic Cloud that orbits around our Milky Way galaxy. And the crime scene here is located in the outskirts of the SMC. Right? Our crime scene is called Supernova Remnant 1E0102.2-7219. Which is quite the mouthful. So we're just going to call it Supernova Remnant E0102. That's what astronomers call it for short. All right. And X-rays at the crime scene reveal that it is the explosive death of a star, a supernova remnant. And the remains of the star were splattered across interstellar space. So was it stellar suicide or was it murder? All right, it wasn't murder, okay? It was suicide, okay? Supernova explosions are when a star blows itself apart. So we actually understand the process of a supernova explosion. There's no mystery there. But there are other questions that remain. Where and when did the explosion occur? And can we locate and identify the stellar corpse? To do that, they called in a specialist named Hubble. All right, Hubble is known for its high resolution measurements that provide invaluable forensic evidence. So this observation right here is from 2003. Hubble also observed it in 2016. And if you look back into the archive, Hubble actually has observations spanning about 20 years of this supernova remnant. And this supernova remnant is expanding, and it's an explosion at millions of miles an hour. So, looking very carefully, they can look to see what's happening. And this is a little movie here. We're going to go into black and white so we can turn it. And we're going to bounce back and forth between epochs. And you can see a tiny little bit of motion, okay? It's tiny motion, but let's zoom in and you can see these gas clouds fleeing the scene of the crime. In particular, they traced 45 knots of ionized oxygen across 19 years to determine the 3D structure of this expanding nebula. The results are that they have a common center of expansion. They can trace these knots motion in 3D back to a common center of expansion. And knowing how fast they're moving, they can figure out how long it took. And they can pin down the time of the explosion at about 1700 years ago, as seen on Earth. However, there's still a problem. If you look carefully at the location, it's empty, right? A supernova should leave behind a neutron star or a black hole, and these should shine in X-rays. But a previously identified X-ray source that's near this isn't quite close enough. It's a little bit too far away. In order for the neutron star or black hole to get a kick and move out that far, it would have to move at a velocity that's just too high for supernova explosions, because it's only got 1700 years to move it. And they say, you know, this doesn't fit with the modus operandi of a supernova explosion. So while we can't end this episode with a triumphant "book 'em, Dano," we can say stay tuned for the next explosive episode as our intrepid astronomical detectives hunt down the stellar corpse of this heavenly body. And now we go to our featured speaker for today. Our speaker today is Laura Prichard. She is a postdoc at the Space Telescope Science Institute. She's been there for 3 years, and she came to us courtesy of the UK. She did her graduate work at the University of Oxford and her undergraduate work at the University of Leeds. And while at the University of Leeds, she was on an exchange program where she actually worked with Raja Guhathakurta, who is the speaker from 2 weeks ago. So she got to go to University of California, Santa Cruz and work there with Raja. And during that, she was extremely lucky. Raja took her to Hawaii to observe on Keck. So she's had quite the experience around it. And I asked her, what has she been doing in the pandemic? And she says, well, she's been cooking a lot. She really likes to cook, and it's been one of her passions, and she's been able to practice a lot. And she's also very passionate about hiking. So I suggested to her she get out to some of the national parks here in the US, because honestly, they're some of the greatest hiking spots. But tonight, she will tell you about the Milky Way versus Andromeda when galaxies collide. Ladies and gentlemen, Dr. Laura Prichard.
Hi, everyone. Thank you so much, Frank, and to the other organizers. It's a real honor to be giving a Space Telescope public lecture. So thank you all for tuning in. One of the main reasons I wanted to give this talk is for my family back in the UK. So they've never actually seen me give a talk on astronomy. And as this one is live streamed, it felt like the perfect opportunity. And as I haven't seen them in over a year, I figured, why not now? So I'm very looking forward to getting my vaccine and hopefully being reunited with them soon. So I work at the Space Telescope Science Institute, and this is based in the wonderful city of Baltimore in Maryland. And if you're regulars at this talk series, you're probably very familiar with Space Telescope and its work, but some of you may also not be. So this is one of the main reasons I live and work in Baltimore. This is the Hubble Space Telescope, and Hubble's science operations are based here at the Space Telescope Science Institute. So anytime you see a gorgeous picture of space, it's almost always from Hubble. And the main reason for that is that Hubble is above the Earth's atmosphere. So it doesn't have to look through clouds, it doesn't have to look through pollution haze, and it doesn't have to look through turbulence in the Earth's atmosphere. This is the same turbulence that you experience if you're on a plane. So it's these kind of bubbles in the atmosphere that actually cause stars to twinkle. So if you go above the Earth's atmosphere, where Hubble is, then you're able to see the night sky in a very crisp way, and these stars appear as very steady beams of light. So Hubble is nowhere near Baltimore or any other city, as you can see. It's 340 miles above the Earth's surface, and it orbits Earth every 95 minutes. So one side note here is that thanks to Hubble, images of space look so incredible now that it can be quite hard to tell the difference between an amazing picture from Hubble and an artist's impression. So the reason I say that is because basically now that images look so good, when we start to talk about scales of space, it can get confusing because you may wonder, well, if that's so far away, how are we able to get such a good picture of it when in fact it's just a beautiful fake image? So in this talk, anytime there is an artist's impression of something in space, I've just made a small note of that. So I study galaxy evolution. And I use the Hubble Space Telescope to do this, and other telescopes on the ground for this. So in this talk, I'm going to go into a little bit of the history of how galaxies were discovered. I'm then going to talk about the different types of galaxies we see and how those are formed. And then I'm going to go into what will happen to our galaxy, the Milky Way, and what that will mean for us here on Earth.
Laura?
Hi.
Do you have YouTube?
You may be wondering why this isn't so obviously seen on a night, say, for example, if you live in Baltimore. Well, one of the main issues that prevents us from being able to observe the night sky is light. So this could be light from lamps or buildings, or it could also be light from the moon. So in order to get the best glimpse of the night sky, you need to step away from artificial light on a clear night when the moon isn't up, and let your eyes adjust for about 15 minutes. And on those very clear nights, you may be able to catch a glimpse of that gorgeous band of the Milky Way running across the night sky. So here is a clearer picture of the Milky Way galaxy. So our galaxy is a spiral disk, and we are in that disk. So when we look out at the rest of our galaxy, we really only see this thin band of light. It's like looking at a dinner plate edge on, for example. Our galaxy is made up of dust, and those dark lanes running through the middle, made up of stars and gas. And those are all held together by gravity. Gravity is the same force that keeps us on Earth and makes things fall to the ground. And it's the same force that keeps us in orbit around the sun and the moon in orbit around us. So this large collection makes up our home, the Milky Way. So the stars that you can see above and below the plane of the galaxy here, those are actually very close to us in the plane of the galaxy. And this glow of light that you can see in the background are actually all of the hundreds of billions of stars that make up our galaxy. They're just so far away that they really kind of look like a fine mist in the background glowing. You may also spot those kind of red patches there. Those are actually heated clouds of hydrogen gas. So that's some of the visible gas that you can see. And you may spot a couple of other interesting objects. And these are the two bluish blobs down to the bottom right-hand corner. And Frank has already actually introduced one of them. So these are the Magellanic Clouds. And you may wonder why you haven't seen these if you live in the Northern Hemisphere. These are only visible from the Southern Hemisphere. So you'd have to head to Australia or South America or Southern Africa to catch a glimpse of the Magellanic Clouds. And as Frank mentioned, these are whole galaxies that orbit our own galaxy, the Milky Way, and they're spiraling in and will one day be fully merged with our own galaxy. So our understanding of the Milky Way, galaxies, and the universe as a whole has come a long way in the last few hundred years. And even huge leaps have been made within the last century. So in the mid to late 1700s, the Herschels, William Herschel and his sister Caroline, made a huge effort to survey the heavens. They made vast leaps forward in telescope design, starting from Newton's original design. And then they also recorded everything they could see over the course of their lives. And this work was continued by William's son, John. Caroline really helped in this effort to develop the modern mathematical approach that we use in astronomy today. And what they noticed in the sky was that alongside the point-like stars, they also found lots of things they called nebulae. This is a Latin word that means mist, and it's basically anything that was not point-like, anything that was fuzzy or irregularly shaped, they called these nebulae. And there was a great debate at the time over the nature of what these nebulae were. And here's some of their original sketches of the things that they were observing through their telescope. So a huge step towards our understanding of what these nebulae actually were came from the vast intellectual leaps of both Thomas Wright in 1750 and Immanuel Kant in 1755. So the Herschels, Wright and Kant were actually all contemporaries working around the same time. So Thomas Wright was a British philosopher, and he first proposed that we are in a massive disk of stars, and that band of light that you see in the night sky is an optical illusion, like we were describing with the thin plane, and we are in that disk there. He then also proposed that the nebulae, Herschel's nebulae, were the same type of thing as our galaxy, but on a whole different plane. So they were termed island universes, because at the time it was thought that our Milky Way really was the whole universe. And so Wright proposed that there were whole other universes, or universes, these are galaxies, in these other planes. And Immanuel Kant, fully acknowledging Wright's breakthrough, continued this work and developed this theory, and he published his results in 1755. Now, this breakthrough is often solely attributed to Immanuel Kant, and there's no denying he was also a brilliant philosopher as well. He was a German philosopher. So these island universes were the topic of much debate. So there's the theory. Does that mean that the case was closed? Hardly, if at all, basically. These theories, when they came out at the time, were widely criticized and discredited. How can you actually prove this theory if you can't measure the distance to the nebulae? So this debate was not solved for another 169 years. But a key breakthrough for really resolving this debate came 153 years later in 1908 by the work of Henrietta Swan-Leavitt. Now, to explain Swan-Leavitt's genius, I'm using the example of a lighthouse. And this lighthouse is a reference to a trip that I made to Nantucket in the summer of 2019, where I gave a similar talk. So my trip to Nantucket was to visit the Maria Mitchell Observatory as an affiliated astronomer. And if you've never heard of Maria Mitchell before, I would highly recommend going to read up about her. She was a fascinating woman, born in 1818, around the time that William Herschel, around the end of William Herschel's career. She was the first professional woman astronomer in America. And this was at a time when even having an education as a woman was a rare thing. She was also a vocal opponent to slavery and segregation, and she admitted non-white students to her school at a time when many schools were still segregated. And she also hosted prominent abolitionists and civil rights activists who had escaped slavery on Nantucket. These were Frederick Douglass, who was born here in Maryland and has ties to Baltimore, and also Sojourner Truth. So an interesting slice of history there. But back to Swan Leavitt and her breakthrough. So here you can see that this lighthouse is flashing. So imagine you're on a ship at night. You know that you must be approaching land soon, and you see this bright flashing light. So you know that that's a lighthouse by the way that it's flashing. So you know that you must be close to land. Now picture that instead you just see a very faint flashing light on the horizon. Well, you know that that's still a lighthouse by the way that it's flashing, but because it's so faint, you know that it must be far away. The key bit of information here is that I know how big a lighthouse should be if I was standing right next to it. Therefore, if it looks very faint, then I can just determine that it's very far away. We do this automatically all the time. If we recognize something or someone far away, just by how big they appear to be, our brain automatically calculates how close they are. So unsurprisingly, lighthouses are relatively scarce in space. But instead, Henrietta Swan Leavitt used a similar principle in order to determine distances. During her work as a human computer at the Harvard Observatory, she found a relation for this special type of variable star. She'd found that by measuring the regularity of the flashes, much like a lighthouse, you could know how big that star was supposed to be. So if you saw that the star was flashing, you could measure how bright it should be. So if it looked very faint, then you could tell that it was really far away. And this was her genius discovery in 1908. In astronomy, this is what we call a standard candle. This is a bright source, and we know how bright it should be. Therefore, we can use that information to determine distance. So this great debate of the nature of nebulae was revived in 1920 between two prominent astronomers at the time, Curtis and Shapley. And this debate was resolved by Edwin Hubble in 1924, a full 169 years after Wright and Kant's original theory. This is less than 100 years ago, and it's amazing to think that even during World War I, humans did not understand the full extent of the universe. They thought that the Milky Way was really all that there was, and they couldn't possibly imagine that it was vaster than our wildest dreams. So Hubble, there's no doubt, discovered some of the most amazing secrets that unlocked our understanding of the universe. But by many accounts, he was not the sharpest astronomer. He arrived at the right place at the right time, and he put in the work to get the discoveries. Hubble arrived to Mount Wilson Observatory in California in 1919, and this coincided with the completion of the 100-inch Hooker telescope, which at the time was the world's largest. Hubble was studying the Great Andromeda Nebula. This is a very diffuse, fuzzy blob on the sky, and it's incredibly faint, so you really need to go to very good observing conditions to be able to see this clearly. And what he was studying in detail, as he was studying this galaxy in detail, and some of you may know where this is going, he discovered some of Swan Leavitt's variable stars, but they were incredibly faint. Using the relation that she found in 1908, Hubble was able to measure the distance to the Great Andromeda Nebula of 1.5 million light years. So we know this now as the Andromeda Galaxy. This was far beyond the reaches of our Milky Way, and it placed it firmly outside to an island of its own, really confirming Wright and Kant's theories of these island universes that we now understand as galaxies. But you'll notice here that it's actually 2.5 million light years away, based on the newer information that we have today and the improved measurements. And this in astronomy is what we call a pretty good guess. It's around the right level. And it was enough to prove this theory that there were these island universes, these galaxies. So this number is so large that it can often be quite hard to wrap your head around what these numbers really mean in astronomy. But I will try and break down what this value really means. So the light that we see from Andromeda on Earth is 2.5 million years old. It's taken that long to travel to us. Light travels incredibly fast, so fast in fact that on Earth it appears nearly instantaneous, but it actually has a maximum fixed speed, and that's 186,000 miles per second. In a year, light can travel 6 trillion miles. That is 6 million miles. And then Andromeda is 2.5 million of those away. So that is a ridiculously large number, and it is really hard to wrap your head around. But even that is incredibly close on the scales of the universe. So when Hubble was working on this, he was receiving a lot of backlash for his work, and this was amidst that great debate. So usually astronomers publish their findings in peer-reviewed articles, present their work to the community, and then that is when the general public would actually be able to hear about that information in the press. In part because of the backlash that Hubble was receiving, he went straight to the New York Times with his discovery in November of 1924. He then presented his results to the American Astronomical Society and the astronomical community on New Year's Day in 1925. So that wasn't all Hubble did. He kept measuring distances to galaxies. Using that same method, using Swan-Leavitt's pulsating stars, he could measure the distance to more distant galaxies. He then also measured their velocities. So this is just speed and also their direction. We can use light from galaxies to measure their velocity and measure if they're moving towards or away from us. So when galaxies give off light, when that light arrives at Earth, that's when we can see that galaxy. And we can capture that light either by taking an image, like the ones that Hubble takes, or you can take something called a spectrum. And this section of spectrum I'm showing in this graphic here is just a very small section of spectrum. It's the rainbow. This is the visible spectrum of light that humans can see. Different chemical elements have different features in a spectrum. And so I'm just showing one example of a feature there, which is just that dark line that you can see in the top panel. I know where that feature should be. So if a galaxy is moving away from us, that light that we receive from the galaxy is actually stretched a little bit. And we know where the feature should be, that's that dashed white line, but then we measure where that feature actually lands, and that's that dark line in the bottom panel. And that shift will tell us the speed of the galaxy. Now, if that feature is shifted towards the red end of the spectrum, this is what we call a redshift. And this means that the galaxy is moving away from us. So what Hubble found was that far beyond our local neighborhood to more distant galaxies, the further a galaxy was away from us, the faster it was moving. Now that is kind of confusing when you think about it, because a lot of Hubble's work was showing that there's nothing special about us, our galaxy and Earth. So then if there's nothing special about us and our location, why then is everything moving away from us? How does it know to travel away from us? And turns out there is nothing special about our location. This is actually a simple geometric effect. So here I'm showing a regular grid of galaxies on the left. So imagine you have this array of galaxies evenly spaced, and this galaxy in the middle here we'll call the Milky Way. Now imagine you expand that grid by a small amount, and those are the orange lines that you see on the right-hand side. All those galaxies on the orange lines are still evenly spaced, and our Milky Way galaxy right in the middle is stayed put. But what you can see is that galaxies a small distance away from that central galaxy have moved a little bit, and galaxies a little bit further away have moved even more, and galaxies towards the edge have moved even further. So what Hubble discovered was that galaxies are flying away from us and our Milky Way, but they're also flying away from all other galaxies. We've now arrived at another major breakthrough in astronomy. What Hubble found was that the universe was expanding. And if the universe is expanding, then it must be expanding from something. Turns out, if you rewind the motion of all of the galaxies back by 13.8 billion years, you get to a point, an instant after time began, where everything that we know in the universe was at a single point. This is the Big Bang Theory, and it was proposed in 1927, and that was kind of built on previous work, and it was confirmed with Hubble's findings and Hubble's law in 1929. Okay, so I'm now going to attempt to answer 3 big questions that I get all the time in astronomy from non-astronomers. But in order to really accept the answers that I'm about to give, you need to first really understand the limitations of the human brain. We humans live on a tiny planet and at human-sized scales. Therefore, we will never be able to fully experience all of the physics within the universe firsthand. And we humans like neat answers. We like things that we can explain, that are satisfying, that make sense to us in the world around us. But in science and in astronomy, the data don't always give you the answers that you want, and you have to be able to accept those answers. So as we go into these following explanations, first accept the limitations of the human brain. So the first question I get asked often is, if the universe is expanding, what is it expanding into? And I think this is actually the wrong way to think about this question. Our universe has 4 dimensions. It has 3 spatial dimensions. We live in a 3-dimensional universe. So to get to any single event within our universe, you need to have 3 spatial coordinates. That could be longitude, latitude, and altitude. It could be X, Y, Z. You need 3 spatial coordinates. And then I also need to know when an event occurred. Therefore, I need to know the time that it happened. That's our 4th dimension. Those dimensions are a property of our universe. And as our universe is expanding, it's also making its own space. So to think of something as outside of the universe doesn't actually make sense, because it's only within the universe that space is a thing. So instead, I like to think of it more as rapid construction. It is creating its space, and as it does, everything within it can spread out a bit more. Okay, second question, equally unsatisfying answer. The next question I get asked a lot of the time is, well, if the universe started 13.8 billion years ago, what was there before? So you'll remember that the 4th dimension of the universe is time. Without time, there is no concept of before. So if you rewind the universe right back to the beginning, there was just the beginning. If you remove the timeline, then you remove any notion of before as we understand it in our limited experiences as humans. And the third question I often get is why? Why the Big Bang? Why us? And my answer to that is, that's not actually my job. At that point, I would point you towards world religions, spirituality, philosophy, and also just acceptance. We may never know, and I'm going to throw it out there, we will never know why we're here. But does it really matter? We exist, and maybe we can just accept that reality and be happy. But I guess I will leave that up to you. Okay, so stepping back a little bit from the more philosophical journey that galaxies can take us on, as I know it can be a bit of a mind boggle. And let's step back into our local environment within the universe. So here, I'm going to show you a video which is made up of all real data, which I really like. It will be a simulated fly through of our local neighborhood in the galaxy. And then it will also show you, get you situated, what's surrounding our galaxy and what's nearby. So here we're starting looking at the plane of the Milky Way, and we're traveling towards the Orion constellation. And you'll notice that the stars within Orion are actually at all different distances. So that's just a projection effect. And we're traveling here towards the Orion Nebula. This is a nursery where stars are born. And you can see that there's another nebula in the background. So these, and that has a dense column of gas in, and that's called the Horsehead Nebula. So these dense columns of gas form stars. And we're traveling towards a third nebula. Now, this is also a nursery for stars, but it's a bit more evolved. This is the Rosette Nebula, and all of its stars have since blown away all the gas and dust, and it creates this gorgeous hollowing out, so kind of like a flower effect. And then we are traveling on to a fourth nebula, but this is different. This, like the one that Frank introduced in the beginning, is actually the site of a supernova. This is the Crab Nebula, and this supernova went off 1,000 years ago. And if you look very closely, you can see the flashing remnant of the dead star. So no mystery there, we can see that pulsar. So here we are, lifting up out of the plane of the Milky Way. And we will never actually make it this far in order to take a picture like this. So you'll see that this galaxy actually turns into a spiral galaxy. This isn't actually our Milky Way, but it's what we think the galaxy might look a bit like. And you'll see the Magellanic Clouds again that we saw earlier. And we now zoom out to the local environment of our galaxy. So we're going to spin around and you will see our massive neighbor, the Andromeda Galaxy, and our smaller neighbor, the Triangulum Galaxy. And we're going to pass through the disk of the Triangulum Galaxy through another star-forming region. And we know that the Andromeda Galaxy is 2.5 million light years from Earth. So you'll notice there are many points of light in the background. Each of these is a whole galaxy. But you'll notice that these aren't evenly distributed. There's a massive clump of galaxies. This is the Virgo cluster. And also you can see that there's massive areas of the sky with really very little in. This is what we call voids. And then you can see these kind of strings of galaxies feeding into that cluster, and these are filaments. So as we now spin around the Virgo cluster, you can see that there are different types of galaxies that we can observe. And as we travel through the filament in towards the center of the cluster, you can see that a lot of the galaxies in that filament in the outskirts are spiral disk galaxies, much like our own and Andromeda. But the closer in we get to the center of the Virgo cluster, the galaxies actually start to change a bit into more of these orbs of stars. And we finish here on the Virgo cluster's brightest cluster galaxy, M87. And that name may be familiar to you. So M87, back in April 2019, the supermassive black hole within M87 became the first to be directly imaged by scientists using the Event Horizon Telescope. So supermassive black holes and their galaxies are a fascinating subject. I won't be going into more detail here, but I highly recommend you check out my colleague's talk, Dr. Mitch Rowolski. He gave a talk in the same series back in December, and he'll be going into a lot more detail on the connection between galaxies and their supermassive black holes. I'd also like to give another plug for a talk, if you haven't already seen it. This was a talk by Raja Gahatakurta just a couple of weeks ago. And as Frank mentioned, Raja was actually a previous supervisor for me back at the University of California, Santa Cruz. So we worked on a couple of different projects, one involving stars in the Milky Way and another involving stars in Andromeda. And this is really Raja's expertise. So you'll notice, given the overlap in our interests, I'll be touching on a couple of similar themes to Raja. But I would definitely recommend going to check out Raja's talk to learn more about our place in the cosmos, black holes, gravitational waves, and also the evolution of the universe from those very early stages through to where we are today. So back to classifying galaxies. So Hubble and others spent a lot of time looking at the different types of galaxies that we see in the universe. And as we saw a little bit in the video, and that's very clear in this image, is that you get different types of galaxies. You get these orbs of stars, and they tend to be more yellow and red. They're like giant footballs, and that applies to both US and UK football. And then in the outskirts, you get to see more spiral galaxies, these intricate galaxies like our own Milky Way. So I like to think of the kind of galaxies towards the center of these massive clusters. That's kind of like city living. So these are busier environments, they're denser, and there tends to be more rapid evolution compared to the field around dense cluster environments. This is more like country living. So slower paced, calmer, and slightly slower evolution. We know that where a human grows up affects their evolution. And the same is true for galaxies. Where a galaxy lives, i.e. how many other galaxies live around it, its environment affects how you get the different shapes and sizes and colors. So how do you actually form these different types of galaxies? Well, this is the study of galaxy evolution that I work on. And this is far from solved, but we do have a few clues. So first, I will go into a couple of very simplistic examples of the differences between these two types of galaxies that we see. Here is a very simplistic model of what one of these elliptical orbs of stars, these elliptical galaxies, looks like. So this is actually a very tiny system, and you can tell it's small because you can actually see all of its individual stars. Now, broadly speaking, you can't, because of the scales of space, you can't actually observe individual stars in other galaxies beyond, say, the brightest in Andromeda. But this very small system is something called a globular cluster, and these exist within spiral galaxies. This one is in our own Milky Way, and it's obviously observed with the Hubble Space Telescope, which is how we get to see it in such great detail. But the reason why I pull this example up to explain elliptical galaxies is you can really clearly see what's happening here. These individual stars are yellow and red. That means they're very small and they're old and they're cool. In astronomy, red means cool. So these are long-lived stars. They've been around for a long time, and you can see there's no dust or gas within this system. It's long since stopped forming stars, and you're really just left with this kind of simple orb of stars. And here is a very simplistic view of what a star-forming galaxy, a spiral galaxy, might look like. So this is not actually a galaxy at all. It's smaller than even the globular cluster we were looking at. This is just one star-forming region within the Magellanic Clouds. So as you can see, these are very beautiful. They contain bright blue stars, really massive stars. And in astronomy, blue is hot. So these massive stars live fast and die young, like James Dean. So they die in millions of years compared to the billions of years of those smaller, redder stars. And as a result, they're often so close to the parent cloud from which they were formed. And they've heated up that material that you can see, and that gas and dust starts to glow. And this is what gives these amazing colors and makes these things so photogenic. So how do we get from these very intricate spiral galaxies with a lot of these star-forming regions and bright blue stars, that's what gives them their kind of overall blue appearance, to these more simplistic, smooth, old systems that we see? Well, the first thing we have to do is remove the dust and gas in those systems so they can stop forming new stars. And one way to do this is to throw two spirals together. So when two spiral galaxies collide, you can get a collision with the gas. This sparks a lot of rapid star formation, and you can use up that fuel very quickly in order to form all new stars. But then that's it. And also, as two galaxies collide, they will be tearing each other apart, and material will be flung out into space. So you can expel a lot of the material as well. So here's a simulation of just that happening. Two spiral galaxies coming together under gravity, tearing each other apart, and they fall together to form one system. But this takes billions of years, which is much longer than a human lifetime. How do we actually know that this process occurs? Well, there's many examples in space And there's fairly damning evidence when you piece together all of the examples that we have. Here's just 4 classic examples. So in space, we can see that there are spiral galaxies very close to each other. We then see spiral galaxies start to interact, but we can still very much tell what they are, but that they're disturbing each other. And then you have something like in the bottom left, where they're just completely tearing each other apart. And you can see these sparks of star formation. And then we have the image in the bottom right there, where you're starting to see something a lot like these old stellar systems. So really just those orb-like yellow-red stars, but you can still see that those spiral arms where the blue stars were formed, you can tell that it was very recently a spiral. So what does this mean for our galaxy, the Milky Way? I told you earlier that the universe is expanding. So why then do galaxies fall together? So this is just an artist's impression of the Milky Way. We will never make it this far as we're stuck within the disk by gravity of the Milky Way. So the forces that hold together the human body are much stronger than the pull of the expansion of the universe. So we as humans aren't expanding. Also, the Earth stays orbiting the same distance around the sun because the forces of gravity on the scale of the solar system are much stronger than the pull of the universe at those scales. And even at larger distances, so like we saw those large collections of galaxies, like in the Virgo cluster, they're all held together by gravity. And that gravity is stronger than the pull of the universe on those scales. So it's all about balancing the scales. At some point, the distances between objects become so large that gravity doesn't become the dominant force, and the pull of the universe, that expansion, can take over as the dominant force. And it's really at those large distances that you start to see things flying apart. And this is what Hubble measured at those great distances. But in our local neighborhood, however, when you look at our large neighbor, Andromeda, we can measure that it is hurtling towards us at 250,000 miles per hour. The pull of gravity is pulling us towards Andromeda, and we are on a direct collision course that will start to occur in around 4 billion years' time. So what will this actually look like? So here's a simulation of that process. You can see that the Milky Way is spinning here, and as we zoom out, we see our neighbors in the local group. We see the Andromeda galaxy, and we see the Triangulum galaxy. So you can see here, Andromeda is hurtling towards the Milky Way, but this is on scales of billions of years. So as the two galaxies begin to interact, you'll see that they do this dance and they start tearing each other apart, and they come together to form one single galaxy. You'll also notice that the color of the galaxy is changing. So this is using up all that dust and gas. So these young hot blue stars are stopping to be formed, and you're left with the light from the red, small, long-lived stars that live for billions of years. And it will just continue to collapse down to form a single galaxy. So what will this amazing process actually look like on Earth, and what will it mean for us on Earth? So here is the band of the Milky Way, the Andromeda galaxy and the Triangulum galaxy. And you can see that in about 3.75 billion years, we are in for a real treat. In 4 billion years, when the two galaxies begin to interact, the sky will change dramatically. And in 6 billion years, the two will collapse together to form a single galaxy with a very comical name that I love, Milkdromeda. So you can see that this process will look amazing from Earth, and it will result in this single galaxy. The night sky will look incredibly different. We will have all new constellations. And this will all occur between the next 4 to 6 billion years. So it's really the gas within these galaxy collisions that make them look so dramatic. And this you can see in the Andromeda galaxy, where these two, in the Antennae galaxy, as I'm showing here, when these two galaxies come together, this collision of the gas sparks this star formation, and it looks very dramatic. But the separation of the stars in galaxies is so great that actually, even in this collision of hundreds of billions or even trillions of stars, it's very unlikely that even two stars will interact. They will likely just sail right past each other. So in order to really grasp the vast scales of space, let's take a look at something more familiar. Let's start with our sun and Earth. So our sun is 4.6 billion years old. Our Earth formed soon after that, around 4.5 billion years ago. And our sun is a very average star. It's in the middle of its life. It's very steady, it's stable, it's one of these long-lived ones, and it's perfect for life. We now know that most stars have at least one planet around them. So that means just within our galaxy, the Milky Way, hundreds of billions of stars, most of them will have at least one planet. Those numbers are huge. So with all of those planets out there, what are the chances that there will be intelligent life within our galaxy? I would say pretty high. But what are the chances that we will actually be able to interact with any intelligent life? I would say that's pretty slim, and here is why. I think often the concept of Earth 2.0 gets talked about a lot, a place that we can go to when this planet dies. And this has certainly been the subject of a lot of sci-fi films. And I think it's good to have goals, but I think it's also good to put this particular goal in context. So let's start with just the nearest stars to us. So our nearest star is a star called Proxima Centauri, and it's actually just this tiny red star just off to the bottom right here. This very small star is 4.2 light years from Earth. It orbits around a double star system, and their names are Alpha Centauri A and B. Does a double star system bring anything to mind for people? So this is Tatooine from Star Wars. And if you live on a planet within a double star system, and that actually may be quite common, you could walk off into a double star sunset, just like Luke Skywalker here. So Proxima Centauri is the third star in this triple star system. And we know that Proxima Centauri has a planet around it, so we can just go there. Well, rather you than me, this is Proxima Centauri and its planet Proxima b. So a reminder that this is an artist's impression. We have not been able to take a picture anywhere like this, and we probably never will. So Proxima Centauri is a very small star. It's around 1/10 of the size of our sun, and it's incredibly unstable. Because it's so small, it's in a constant battle to produce enough radiative energy to be able to support its own weight under gravity. So it's constantly fluctuating, and as a result, it regularly produces massive flares of dangerous radiation. And with Proxima b being as close as it is to the star, if any life might have lived there in the past, it's long since been fried. So we know that this is a highly inhospitable planet to humans. And this is like a hot, dusty rock. So a far cry from our oasis here on Earth. I imagine Proxima b to be something like this scene from Mad Max with these kind of massive dust storms that you get. So, you know, not ideal, but hey, just if we wanted to go and check it out, how long would it take to get there? So I think first it's important to figure out how far have we gone so far? Well, the furthest man-made object from Earth is the Voyager 1 spacecraft. This was launched in 1977. And towards the end of its mission, it turned around and took one final image, this time of Earth in 1990. And this was famously requested by Carl Sagan, the astronomer and author. This is the pale blue dot image. This image was taken 3.7 billion miles from Earth. So that was in 1990. How far have we made it so far? Well, today, Voyager 1 is 14.2 billion miles from Earth. This is 1/500th of a light year. So this is still a long way to go to make it just to 1 light year, let alone the 4.2 needed to get to Proxima b. But, you know, if we still wanted to go ahead with this, how long would it take to get to Proxima b? Well, we currently don't have the technology to get there. So the first thing we'd need are major technological advances for both energy generation in the depths of space and also technology advances to sustain human life on a very long interstellar journey. But say, for example, we very ambitiously figured this out in the next 1,000 years. How long would it take to get there? Well, that would depend on how fast we traveled. So what is the fastest thing that humans have ever produced? Well, this is the fastest man-made object. This is an amazing mission, NASA's Parker Solar Probe. This was launched in 2018, and it's a car-sized robot that's orbiting the sun and taking data. On the 21st of January, 2021, so just recently, it completed its 7th orbit of a total of 24 planned, and it reached a near 290,000 miles per hour, completely smashing previous records. At its peak, the Parker Solar Probe will reach 430,000 miles per hour. This is almost double the speed that Andromeda is moving towards us, and I think that's absolutely incredible. It's such a cool mission. But NASA's Parker Solar Probe doesn't need to stop. It's a death mission. It will burn up, unmanned, of course. It will burn up in the sun. And the hardest thing is slowing down. It is using the sun's gravity like a slingshot to speed up, but it would also take the same amount of energy to slow down. And that's something we have not figured out how to do, again, in those deep areas in space. But, you know, in theory, if we could get a massive spacecraft to move at this incredibly ambitious speed, we'd probably have to go a lot slower, but, you know, just saying, how long would it take to do this journey? Well, to get to Proxima b, our closest planet, it would take 7,000 years to travel those 4.2 light years. Now, if we were traveling at the speed of Voyager 1, this journey would actually be over 70,000 years. This very optimistic journey length, that would be about 200 to 300 generations of humans on board one spacecraft. And even if we wanted to do it unmanned, that would be an incredibly long time to wait for any sort of information, particularly when we already know this planet is inhospitable to life and us humans. So we already know that one's a bit of a dud. So how about we try maybe a more promising star? Well, if we take Vega, for example, Vega appeared in Carl Sagan's book and the film Contact, which is one of my favorites. Using our incredibly ambitious speed, it would take over 40,000 years to reach the star of Vega. So you can see that these scales are vast in comparison to the length of a human life. So this may not be a viable backup plan for the future of humanity. So even if we just scrap the whole travel idea and just wanted to send a message, that message could travel at the speed of light. But even to get a message from one side of our galaxy to the other side of the galaxy, let alone all the billions, thousands of billions of galaxies within our universe, even just to go across our galaxy would take 100,000 years to send that message. Now, it's likely that aliens may find us at some point. But if we were to send that message, it would then take that same amount of time to get a reply. So even if aliens might be listening in on us, given that the first radio signal was sent in the late 1800s, all of the information that we have inadvertently pumped into space since then, all of those messages have only made it around 100 light years or so, so still only about 1,000th of the distance across our galaxy. I would like to highlight, however, this very new exciting discovery. by researchers at the University of Hawaii. They discovered this planet, shown in this artist's impression, TOI 561b. This planet is 280 light years from Earth. So if we were using our very ambitious speed, this would be a mere 440,000 year long journey. This planet is 1.5 times the size of Earth, and they found that it has a staggering age of 10 billion years. That's almost double Earth. So when you think about that the universe is 13.8 billion years old, our galaxy started forming about 12 billion years ago, and this planet started forming pretty soon after that. While we know that this particular planet is an inhospitable rocky lava ball and it orbits its star every 10.5 hours compared to our leisurely 365 days, it does mean something bigger in the context of when planets might have formed in this galaxy. It could mean that there were advanced, intelligent civilizations out there billions of years ago. And just to think how far we've come in Earth's 4.5 billion years, from bacteria in the primordial soup to conscious beings studying the universe with iPhones in hand, it's amazing to think what an extra few billion years can mean for advanced civilizations. So while our prospects of interstellar travel aren't looking so hopeful on any sort of reasonable timescale, given the distances and scales of space, it's still something we can aim towards and put the groundwork in for. But I don't want us to rely on finding an Earth 2.0 when this planet dies, but instead to really appreciate the gorgeous planet that we have, that we are perfectly adapted for already. So what will happen to Earth in 4 billion years when Andromeda and the Milky Way begin to collide? Well, not a whole lot really. As we've seen the vast distances of space, stars will most likely just sail right past us and we will settle in a new galaxy, Milkdromeda. Those stars will likely be as far away from us as they are now, which we know is very far. There is a small chance we could be one of those stars that's flung out into space, but our Earth will still stay in orbit around the sun. The forces of gravity in our solar system will be able to withstand that, and that would actually be a relatively slow process. We would just drift off into the abyss. But you may remember that I told you that the sun is halfway through its lifetime. In 5 billion years, the sun will begin to die. So about halfway through this collision with Andromeda. And in 5 billion years, the sun will swell up to what we call the red giant, and it will actually engulf the Earth. So while that may sound scary, this is all a long way off in the future, and we will be long gone. If we are fortunate to have any descendant species, they will likely be as different from us as we are from the bacteria in the primordial soup. So this may sound like doomsday, but maybe they will figure out interstellar travel and maybe they will find a new planet, and who knows what will be waiting for them there. But first, we have another major issue to attend to. I would like to focus on the incredible planet that we have and to really emphasize the importance of addressing our current climate and ecological emergency that we are in. This is the biggest threat to human life that we face. If the goal of any life form is to survive, then we are currently working against our best interests by killing our habitat. And that is not a great look for a species that believes it's the most intelligent on Earth. If we continue as we have been, future generations will never make it anywhere near to even the closest star. We are on a rapid course for irreversible, extensive damage to the Earth within my lifetime. But this catastrophe can be avoided. The only way for human life to survive and give way to this next generation of beings is to learn to thrive on Earth sustainably. I'd like to highlight this recent quote by Greta Thunberg in her address to the World Economic Forum. "You can't negotiate with physics." This is happening. It's a dire situation, and we have to face that reality. The time for discussion is long gone. We have to take action now, and I believe it's everyone's responsibility to contribute to that action. A very small suggested step that I'd like to highlight here is what the Earth is asking of us in this slide. And this is to watch David Attenborough's new documentary on Netflix, A Life on Our Planet, as a small suggested first step. This is a great film that draws on current science to really highlight the urgency of acting now, but also offers a surprisingly simple and hopeful path forward for reversing our course towards mass extinction. And I think it's a great first step if you haven't already seen it. We as individuals can often feel helpless, but if you only take one thing from this talk, it's that you can make a difference. By voting in the planet's best interests, by spending, investing, eating, and living in the planet's best interests, you can save the future of humanity. So in the last couple of slides, I will just bring the focus back to astronomy, and I'd like to advertise the upcoming James Webb Space Telescope. This is set for launch in October of this year, on Halloween actually, and Hubble's flight and science operations will be run from Baltimore at the Space Telescope Science Institute. So James Webb will have a direct line of communication with the scientist here in Baltimore. So James Webb is really set to revolutionize our understanding of the universe from planets through to those very early stages in the Big Bang, and also how galaxies formed. We'll be able to fill in so many gaps that we currently don't know the answers for. James Webb will have a large 21-foot wide mirror, and it will also be an infrared telescope. Now, the sun is actually a very bright infrared source, and so Webb will actually be always facing away from the sun with these giant sun shields. These are about the size of a tennis court. And unlike Hubble that orbits the Earth, James Webb will actually be orbiting the sun. It will be traveling around the sun at the same speed as Earth, so kind of constantly in its shadow. So you can see here in this artist's impression, at the bottom left-hand corner, you can see the very small Earth and with the moon orbiting, and then the sun off to the distance a little bit further. So why infrared? Well, here's an example of the benefits of using a different wavelength of light. So these are two images from Hubble, both in the optical on the left and in the near infrared on the right. And this is of the pillars of creation, stellar nurseries within the Eagle Nebula. So on the left, you can see the dust and gas from where the stars are formed, but it's actually obscuring a lot of the light. And when we look at the infrared, we can pierce through those dark shields in order to reveal new, exciting physics. So James Webb will actually be in the infrared to much further wavelengths than Hubble can go. And this means that we will be able to observe the faintest and most distant objects in the universe to really understand how those very early stages of galaxies formed, and also to reveal new planets as well. So thank you so much for listening, and I'll be very happy to answer any questions.
All right. Thank you, Laura. And I'm actually going to start with a comment from the chat that actually reflected my own thoughts. It said, I can't remember who this was. Wow, we've come a long way in 100 years.
Yeah.
And I think that's, to me, that's exactly what your talk has done, because it started back when we only had one galaxy and it was the entire universe, and goes out to sort of really explain just how much we've learned about galaxies in the last 100 years.
Yeah.
So let's see, there were a ton of questions here, and Grant and I are going to have a heck of a time trying to figure out the best ones. But there were a lot of questions about, all right, are we really not going to get messed up by this collision, okay? We always get this question about galaxy collisions, and somebody put it strongly like, hey, we're going to collide at 250,000 miles per hour and we won't be messed up. What's going on here? Can you just attack that just one more time?
Yeah, it's a very good point. And it really goes back to those scales of space. So yes, gravity is an amazing force, and it's really driving these two monsters together, and will completely kind of, reshape them into one new amazingly named final galaxy, Milkdromeda. But really the separation between those stars means that the kind of the influence of that star, its planets, it's so close. We are so close to our sun compared to those really vast distances in space, that those stars will likely just really kind of smoothly pass by each other. But there is an interesting component there. There is gas, and while this gas and dust, it's not quite like the dust you would find in your house. This dust is like a very fine smoke. It's a very fine mist. So maybe this might kind of have some effect, maybe if that's kind of raining down on the Earth's atmosphere. But we have this pretty great shield around the Earth's atmosphere of our magnetic field. So really those effects will be relatively minor. And as I mentioned, in 5 billion years, we'll have something else to be worrying about in that the sun will be engulfing the Earth anyway. So it's who knows what's going to get us first, but
hopefully we'll figure out how to move to Titan first, right? Or something like that.
Yeah, that could work out. Yeah.
Okay, so Grant, let me bring Grant Justice in. He's been following the chat and answering a few questions in the chat. Grant, I always love your NASA shirt. What questions
I gotta fit the theme
for our speaker today?
All right. So I'll get started because I will never not take an opportunity to have us harp or talk up James Webb. Somebody wanted to see if it's true that we cannot see through things like the Milky Way or nebulae or like large dust clouds or what have you. And since this is a James Webb thing, figured we could talk about it. So.
Yeah, so using those optical wavelengths, so what we can see with our eyes, a lot of stuff is just obscured from us. But if we move to those redder wavelengths, like I showed in that last slide, you can pierce through a lot of that material, and you can start to see objects on the other side of that dust and gas, and even within those clouds. So it's really using those longer wavelengths that we've built up a pretty amazing three-dimensional view of what our galaxy looks like. We can measure, where the stars are in those spiral arms, and we can see where that gas is and everything like that. So we have this kind of, we put on our infrared goggles, and we can see through, and we can see more of the structure. So it's really using those longer wavelengths, and James Webb will really just open up a whole new area of space, and you're going to see some amazing images come from Space Telescope and the team here. It's going to be awesome when we start to see some of the things that we haven't seen before.
Okay, that sounds good. What next?
Solid. So next up, I'll say, can we measure lateral motion? How many, and by that I think the person meant, how many axes can we actually track motion in these celestial objects? Like obviously it's space, so there's multiple, yes.
And Grant, I think that was specifically in terms of the Andromeda galaxy, wasn't that?
Yes, that was specifically in terms of Andromeda.
So thank you for asking. I actually did have a section of my talk on the sideways motion of Andromeda, but I cut it because it does go into a bit more detail. So in theory, yes, Andromeda is hurtling towards us at this great speed. But what if it was also traveling sideways at an even greater speed? It could really mean that we're not going to collide with Andromeda anytime soon, and it may do kind of a slow spiral in. But using the Hubble Space Telescope, researchers at Space Telescope actually measured the speeds of, I think it's maybe thousands, maybe hundreds of thousands of stars in Andromeda. They measured the micro shifts in those stars and said, how fast is Andromeda moving that way on the sky? The measurement they made is so freakily accurate. It's one of the most accurate measurements made in astronomy. I figured it out a long time ago. It was something like, if you were on the International Space Station orbiting Earth, it would be like being able to measure like the growth rate of a human hair. It's wild. But what they found is that Andromeda isn't really moving sideways. It's on a direct collision course. It's coming straight towards us. So yes, we can measure those lateral motions in space. And some amazing scientists did with Hubble. And yeah, it's coming straight for us.
Right. This relates to what I did in the news summary, talking about taking Hubble observations 20 years apart and being able to see those really, really, really tiny motions. Now, in what I showed, you could actually physically see them with the eye. This was so small that you had to use computers to actually go in and very finely measure them. And I will note for the audience that what my background here is actually an image of stars in Andromeda. The globular cluster over here, that's a globular cluster in the Andromeda galaxy, not in the Milky Way. I just loved this image because it was like, whoa. I mean, we're seeing what Hubble would have, given his eye teeth to be able to see.
Yeah, and this was all part of a massive survey of Andromeda that Raja was involved with, to the FAT survey, which I think is a great name, the Panchromatic Hubble Andromeda Treasury. So it's really using the huge data set there that they could then measure those micro shifts over a period of time, as Frank mentioned.
All right, I'm sure we have more questions.
Yes, very much so. All right, so how can you tell?
I said I mentioned aliens on YouTube, so I'm not surprised that there's been.
We'll avoid those. We'll avoid those questions.
We'll avoid those. How can you tell Cepheid variables apart from other stars that pulsate or are variable in other ways that you can identify them?
This is an excellent question, and one that actually it is quite hard to tell. There are some variable stars that vary, but not on kind of any regular time scale. So there are different types of stars, Mira variable stars. I did a project on those in Andromeda. So basically, spectra are your friend here. When you can measure a spectrum of light, you can look out for the chemical signatures within stars to be able to kind of tell what they are. You can tell kind of how big they are and their mass. And so that's one way that you can tell exactly what that type of star is. But in those early days when Hubble was really just measuring the pulsing variable stars, he, broadly said, we're just going to say they're regular. And he got a pretty good measurement, but obviously now that we know more, there's some variable stars that can muddy the waters in there.
And in fact, Hubble got the wrong type of variable star. So he measured it as being like 500 kilometers per second instead of 100 or 50 kilometers per second, right? If I remember correctly, there's a type 1 and a type 2, as astronomers always seem to do. He thought it was this one and it was another one. But he proved that it was an external galaxy. First of all, that was the big thing. And then the number had to then, of course, be refined for the Hubble constant there.
Yeah, good enough. And in astronomy, order of magnitude. If you're in the right ballpark, you can
Yes.
certainly rule out some things. You can rule out that Andromeda is just sat in the halo of the Milky Way.
Right. I keep trying to tell my wife that, factor of 2 is good enough for me. What else we got, Grant?
All right, so I'll take one. I'll get us one more, and depending on how we go here, I have an extra. This one's a little bit more out there, which is if mass and time are linked, would larger objects be more affected by time and or gravity than smaller objects?
Mass and time are linked? I don't know that I understand.
Meaning, what effect? I think what this person is trying to say is, what effect does our perception of celestial objects get affected over distance by time and gravity in both lensing with the telescopes and in how we can observe them over distance. Because I know we use some of that with adjusting for like gravitational lensing, and in the cases of things that are very far out there, we can also use some of that to establish the constant motion. But are those two things linked in any way, and how do they help us with our science?
Yeah, so I mean, I think for this, if I understand the question correctly, we tend to rely pretty heavily on relativity for this. So that link between mass and time, because time is actually quite a flexible number. And so the heavier the gravitational well you're in, the slower the time goes. And so, yeah, we have to adjust for mass and time in some calculations when you're thinking about gravitational lenses. You have to adjust for this even when you're thinking about GPS systems and how they all have to make that correction. So if I think I've understood the question, okay, but yeah, so yes, we always have to factor those in, and the heavier objects will always have those effects more because of that relation.
And I would just add, because there was a lot of conversation in the chat about this, that this is a localized effect on the massive objects. It doesn't really affect global. When you compute a cosmology, you're not necessarily having to deal with that on that. It's really with the localized effects where you have the high concentrations of mass that will take care of that. Let's see, I think we have time for one more question.
I have one more,
okay.
And it's a good one, unless you have one as well.
I have one as well.
Mine's real quick.
No, it's real quick. I gotta let you do your job.
Okay, all right. Dr. Laura, what is your favorite star in Andromeda?
Wow. Well, they don't have names, so it's quite hard to tell. But so the project that I did with Raja, actually, I was looking at stars that had emission lines. So like those features in the spectrum. So we were looking at lots of these bright blue stars, these massive hot stars that were giving off these kind of beacons of light that we could be able to tell what they were. So I really like that collection of stars. So some of them were Mira variables, so a different type of variable star. And some of them were massive, really massive, bright, hot blue stars. And they're spinning so fast that they don't look round. They actually look oblate. And so they're really kind of like, squished footballs, rugby balls, if you will. That helps with my analogy of football.
That's really cool. And as I'll pass on from the chat before I turn it over to Frank to bring us home, everyone has been very pleased with your analogies. They say thank you. It made it much easier to understand.
Great, thank you. Thank you everyone for that comment. I'm glad anything was clear. So
all right. Yeah, so
all right,
we are up against our limit. We cut off after 90 minutes and we hit that. Thank you again, Laura. This was wonderful, and I'm sure you're going to get lots of views on YouTube because and people watching it over and over again to go, I didn't get that. I got to watch that again to really let that sink in, because some of this is mind blowing. We will be back on March 2nd with Tom Brown talking about the Hubble Space Telescope, from cosmological concept to alien atmospheres. He's going to mention aliens too. So we'll have a great chat back then. Thank you all for attending, and have a great day.
Bye.